All right, so last time we started talking about kinematics and kinetics of particles. You know, recently in this class we've been doing kinetics and kinematics of rigid bodies. Now we're going back to particles. In rotating coordinate systems. And we've had three big results, three main results. The first one is for any vector u measured in a rotating coordinate system, the time derivative of u is equal to the time derivatives of the components of u plus this correction term that's equal to the angular velocity of the coordinate system crossed with the u vector. Second, we applied that rule, and this is the, before I go on, this vector, ux dot, uy dot, uz dot, you can also think of as the u dot that's observed in the rotating coordinate system. Second, we applied that first major result to the position vector to get an expression for the velocity vector. And you get that the velocity vector, which is just p dot, is equal to the time derivatives of the components of the position vector plus the angular velocity of the coordinate system crossed with the position vector. And you can also think of this as v, which is equal to p dot, is equal to the velocity observed in the rotating coordinate system plus omega cross p. And then the third main result, this is the one that's going to be most important to us because it relates to acceleration. And acceleration is how you, is where the path is to get from kinematic quantities to force quantities through Newton's laws. You know how, like, if you're in the McPhail Center downtown and you need to get to the Hyatt or whatever, like, you know you can get from one to the other, but first you have to get to the floor the skyway's on. Acceleration is where the skyway is. Okay? You got the kinematic stuff, you just need to go to the skyway. I don't know if there's a skyway between those two buildings. I don't even know. I'm sure there's not. Still, I'm sure you know what I'm talking about. And then the third one is apply number 1 to the velocity vector to get the acceleration vector. And you get that the acceleration, which is equal to v dot, which is equal to p double dot, is equal to the components of position double dot plus omega dot cross p plus 2 times omega cross the components of position dot plus omega cross p. And another way you can think of this is that the acceleration is equal to the acceleration vector observed in the rotating coordinate system plus omega dot cross the position vector plus 2 times omega crossed with the velocity vector that's observed in the rotating coordinate system plus omega cross quantity omega cross p. Okay, so those are the 3 big results. And I want you to notice kind of at the heart of all this is that now that we have this rotating coordinate system, p double dot is not the same thing as the double dots of the components of p. Okay? All of this stuff beyond, except for this components double dot, all the rest of it is that correction factor that this whole topic is about. Okay? If you have a non-rotating coordinate system, p double dot is equal to components double dot. But with the rotating coordinate system, you also have to deal with those, with the terms that relate to the I dot, j dot, and k dot. Those are non-zero, and that's what all this deals with, that correction term. Okay, so now I want to think a little bit about compare these 2 equations that sort of look similar but do different things. One is the watermelon equation. So that says that the acceleration is equal to alpha cross r plus little omega cross quantity little omega cross r. And the second equation is A is equal to components double dot I'm tricking you into writing this equation a whole bunch of times. You wouldn't have even noticed if I wouldn't have just said that. Plus omega dot, capital Omega dot, cross P, plus 2 times capital Omega cross P components dot, plus capital Omega cross quantity capital Omega cross P. Okay. They have different numbers of terms, but the terms, they share terms that look pretty similar. So here are the terms that we need to sort of make an effort to understand. Those are obviously very similar looking. Alpha is the time derivative of lowercase omega. So those are saying the same thing. And then these two are obviously pretty similar looking. So let's go into that a little bit. Okay, so things to notice about these. The first one has to do with lowercase omega versus uppercase omega. Lowercase omega is the angular velocity of a rigid body expressed in an inertial coordinate system. Or actually, just be a little more inclusive, it's actually the angular velocity of a rigid body in a non-rotating coordinate system. Capital Omega is the angular velocity of the coordinate system itself relative to, something fixed. The second thing is comparing alpha to capital Omega dot. Lowercase alpha is the angular acceleration of a rigid body in a non-rotating coordinate system. Capital Omega dot is the angular acceleration of the coordinate system relative to fixed, relative to the true ground. The third difference, anybody have any questions yet? The third difference is the r vector versus the p vector. These are also very similar, but kind of subtly different. So r is a vector from the center of a rotation of a rigid body to the desired point. P is the position vector of the desired point, which means You know, in other words, that's a vector from the coordinate system's origin to the desired point. Okay, so to calculate r, you're going from the center of a rotation to the desired point. To calculate p, you're always going from the origin to the desired point. So now, I've been sort of already emphasizing this, but the components dot and the components double dot are the velocity and acceleration, you know, respectively, that are observed in the rotating coordinate system. So they're not the true V and A. P is a little different, and I'm going to put that in the same one. P is the position vector observed in the rotating coordinate system, and it's also the true position vector. And the reason for that is that you don't have to take any derivatives to get the position vector. So those are the same thing, okay? Now you can think of this term as like an unobserved, let me word it a little different, sorry. That's the tangential acceleration that's unobserved in the rotating coordinate system. Capital omega cross quantity, capital omega cross p is the centripetal acceleration that's unobserved in the rotating coordinate system. Okay, so now I'm going through this 5, 6, and 7. I'm going through a list of the correction terms. Okay, so if we're looking at this expression for the acceleration in a rotating coordinate system, here is what we're used to calling the acceleration. Here are the 3 correction terms. I talked about this one. That's like an unobserved tangential acceleration. I talked about this one. That's an unobserved centripetal acceleration. And then there's this third one that doesn't look familiar informed anything. That's called the Coriolis acceleration. How far? Okay. So 2 times capital omega cross components dot is called the Coriolis acceleration. And I don't know, that actually that term comes up occasionally in like TV shows or whatever. It tends to be so that Coriolis acceleration, I believe, is the one that, have you heard of the Foucault pendulum? I think somewhere in France there's this gigantic pendulum that with careful markings on the floor, and you can actually, what? Yeah, okay, so oh, okay. I guess that makes sense, yeah. And so you can see that as this thing rotates, just little by little over the course of the day, the direction that it's swinging just changes slightly. That line just keeps moving. And that's a measure of the Coriolis acceleration that comes from the Earth rotating. You know, for anything without super precise calculations, for almost any kind of experiment, the Earth is essentially a non-rotating coordinate system, and also its origin is essentially non-accelerating. But if yeah, really? Huh. I didn't know that. I'll have to check that out. So, but of course it is rotating, just not very fast, and it is accelerating, just not that much. And with careful measurements, you can see that your measured acceleration doesn't quite explain what's happening when you put it into Newton's laws. Yeah.
I think so.
In St. Paul?
Yeah, I think it knocks down a block every half hour.
Huh. I'll have to check that out. That's awesome. Yeah, we should take a field trip.
Do we need our parents' concession for that?
I think probably any of you under 18. Anyone under 18? Kenny? Also, we need chaperones, if any of your parents would be willing to.
Tie us with like the rope and make sure that like follows the
These are all good ideas. Yeah, right. Well, okay, so the next thing I want to do is an example of try to demonstrate how this comes into calculations. I call this astronaut 3 ways, but it just occurred to me this morning that sort of has obscene connotations, so I'm not going to call it that. So 3 ways to calculate the acceleration of the unhappy astronaut. Okay, so here's the setup. There's the astronaut. This arm is whipping around in a circular motion. And let's say the astronaut has a mass of 60 kilograms. And let's say this arm is 5 meters long. Our coordinate system is going to, well, we're going to deal with coordinate systems in 2 locations, and actually 3 different coordinate systems. One is going to have its origin here. So this is y, this is z, x is coming out towards us. I'll call that origin A. And another one is going to be at the astronaut's center of mass. There's y, there's z, I'll call this one B. And the arm is rotating with a constant angular velocity of, you can see this is counterclockwise about the y-axis, pi radians per second. And so we're going to calculate the force applied to the astronaut by the seat three ways. The first one is for a coordinate system located at A, but fixed. So it's non-rotating. And so that coordinate system, according to that coordinate system, once every revolution, it just sees like, ah, you know, help me. But it only sees the person once every revolution. Okay? Yeah, exactly. Exactly. The second one is a coordinate system located at A, so that origin is the same, but rotating with the arm. Okay, so what does that coordinate system see? It just sees a guy sitting there going like, oh, for the love of God, turn it off! Ah! Just the whole time it's just tracking him, you know. And then the third one is a coordinate system located at B, rotating with the arm. So what does that one see? That one just sees somewhere inside his chest the whole time. Just it's located at his center of mass. So it's just traveling around. Nothing changes with that coordinate system either. Okay? So all of these numbers are going to, you know, the approach for each of these is going to change. But obviously, if we're doing this right, we need to measure the same acceleration for the person in each of these three cases, and therefore the same forces. Okay. Okay, so the first one, this is the warm-up one. We've done these a bunch of times before. So this one you can think of, this is a circular motion of a particle. We have a coordinate system located, oriented like this. There's Z, there's X, and here's the particle at a certain instant. It's rotating this way with an angular velocity of pi radians per second. Okay, so what do we have to do to calculate that acceleration? Yep, right. So I'll call the astronaut P for Pete. So the acceleration of Pete is equal to angular acceleration cross r plus lowercase omega cross quantity lowercase omega cross r. This is a constant angular velocity, so this one goes away. What's the angular velocity? Okay, but it needs to be a vector. Positive y, yep. So 0, pi, 0. And then what's the r vector?
0, -5, or 5.
5, yep. 0, 0, 5, yep, exactly. So the acceleration is equal to 0, pi, 0, cross quantity 0, pi, 0, cross 0, 0, 5. And that is 0, 0, -5 pi squared. Okay, so Newton's second law we have the weight, that's 60 g, so 588.86. And then we have the force on Pete by the chair. And those are the only forces. That's not Newton's second law, that's a free body diagram. I hope I said 60. I might have said 6, but I wrote 60. That no human adult.
Oh, but 60, then you're off that after 10. It's 588.
Oh, yeah. Yes, thank you. So Newton's second law says FPC plus the weight is acting in the negative y direction. This should say plus. 0, -588.60 is equal to the mass times 0, 0, -5 pi squared. And so FPC is equal to 0, 588.6, negative 300 pi squared newtons, which is about equal to 0, 588.6, negative 2960. Okay, any questions about that calculation? That's just circular motion. So we've done those a bunch of times. Now we're going to go to the coordinate systems that are non-inertial. We're going to start out with one that's just rotating, and then we're going to go to one that's rotating and has an accelerating origin. So B, coordinate system fixed at that point A, well, the origin is at A, but rotating with the arm. Okay, so for this one, our acceleration is going to be equal to the observed acceleration, or I'll write it like this, plus capital Omega dot cross position vector, plus 2 times capital Omega cross with the observed velocity vector, that's the components dot, plus capital Omega cross quantity capital Omega cross P. Okay, so let's think about what all these terms are. So first of all, I guess let's go through the position, the observed velocity, and the observed acceleration. What's the position vector going to be at this instant? That's right. So the origin is here, so the astronaut's position is 0, 0, 5. Okay? I hope you're with me on that, because that's the easiest one of these to figure out. Okay, so an instant before that, what was the position vector observed in that rotating coordinate system? 0, 0, 5. 40 seconds before. I don't know if they make this guy do this for 40 seconds. I hope not. But if they did, it would be 0, 0, 5. So what does that say about the velocity that's observed in the... that's right. Since that position vector isn't changing over time, according to that coordinate system, the velocity is equal to 0. So the velocity observed in the rotating coordinate system, which is what we can also call the components dot, is 0. And so what's the acceleration observed in the rotating coordinate system? That's also 0. And that's the component's double dot.
Would it be wrong to write that as a vector double dot?
Yes, it is, because the vector double dot is actually equal to the acceleration. So yeah, it's sort of a pain in the butt to write. But yeah, it never stops being true that the second time derivative of the position vector is equal to the acceleration. That's always true. It's just that now the second time derivative of the position also includes these other terms that we haven't dealt with up until now. So this is only a piece of it. Okay. What else do we need? We need the angular velocity of the coordinate system. So what's the angular velocity of the coordinate system according to something fixed?
5 radians per second.
Yep. And in about what axis? Yep. So this, our capital omega in this case is the same thing that our lowercase omega was in the last problem. That coordinate system is rotating according to this, 0, pi, 0. And the last thing we need is capital omega dot. What's capital omega dot? In other words, what's the angular acceleration of the coordinate system? That's 0, yeah. Okay, so now we can set this up. The acceleration of p is equal to the observed acceleration in that rotating coordinate system, which is equal to 0. What?
Like when you're putting everything back,
Mm-hmm.
like who would get it?
Oh, a bunch of things are going to go away. Yeah. So it'll make sense when you look back at this. In our original circular motion problem, all we had was centripetal acceleration. So the only term we're going to have in this is an unobserved centripetal acceleration that doesn't appear to the coordinate system, but appears because of the rotation of the coordinate system. It'll get more complicated in the third example that I guess we'll have to do for whatever day is next, Friday. Okay, so now capital omega dot is 0, 0, 0. And we take the cross product with the position vector. So this goes away. This goes away. Then the third term is 2 times omega crossed with the observed velocity vector, which is 0. So that goes away. And all we have left is, this should be plus omega crossed with the quantity 0, pi 0, crossed with the position vector 0, 0, 5. And so mathematically we come up with the same expression for different reasons. And we come up with 0, 0, negative 5 pi squared. That acceleration matches the last one. And so the free body, so what changes about the free body diagram in the non-rotating coordinate system? It's a trick question. Nothing changes, but I just want you to be clear on that, you know. Forces are forces, of courses. Okay? So 588.6, then this unknown force on Pete by the chair. And so Newton's second law looks just like it did before. We have FPC plus 0, negative 588.6 88.60. Those are the only forces. And those are equal to the mass times the acceleration vector. So FPC is equal to 0, 588.6, negative 2960 newtons. And you can, it's probably not too hard to imagine why the ability to do this is useful, because you don't always have perfect control of where you can put the camera that's taking your measurements, and the camera that represents your coordinate system. If you're doing space calculations on what's happening inside some kind of spacecraft or whatever, or some kind of, any kind of aircraft, you don't have the ability to mount inertial coordinate systems out in space and for where the thing's going. You have to mount them inside this thing. But what this is saying is you have the ability with this approach to take the measurements that you get in your, this thing that's rotating and accelerating, and then correct them back into an inertial frame of reference where you can use Newton's laws. Yeah, thank you. That's what I was waiting for. Okay, that's it.